Hello, it's Professor Todd Elliott again, and this video I will introduce to you semiconductor theory, doping, and basic biasing. Today is Sunday, May the 4th, 2025. These slides I originally made, I don't know, 25 years ago? Yeah, too bad you can't see the gray hair, but anyway, I hope you enjoy it. Okay, so semiconductor is a device which shares the property of both a conductor and an insulator. And the tremendous advantages is we can change the properties to go between one and the other. So a semiconductor can either act like an ideal conductor, although not truly, or an ideal insulator, but that's not quite true either. So it's adjustable, changeable, controllable. Okay, and so all electronic devices, they're all semiconductors. Okay, so diodes, transistors, microcontrollers, CPU, that's all semiconductors. Okay, so this is the very foundation of that. So a semiconductor is a device which is neither an ideal conductor or insulator. Common devices include diodes, transistors, SCRs, etc., etc. The silicon atom and semiconductors are primarily made up of silicon. Germanium's not that popular anymore, but the way technology is changing, who knows what's going to be developed tomorrow. But anyway, for the silicon atom, we can see we can have the nucleus, and inside the nucleus we have 14 protons, and we have 1, 2, 3 orbital shells. Each one of those orbital shells contains a specific number of electrons, and in the outer shell, a silicon atom has 4 electrons, which means is that there's plenty of space in which it can temporarily borrow, accept additional electrons from neighboring silicon atoms to create a current flow. Okay. So when you talk about semiconductors, you talk about, eventually you're going to run into the term doping. Doping means the adding impurities, arsenic, phosphorus, boron, etc., to increase the number of electrons. Electrons have small negative charges, or holes. What's a hole? A hole is an area with a slight positive charge because there's not an electron there currently. Okay. Mini golfing, right? Think of the golf ball as the electron and the cup as the hole. When the ball is not in the cup is absent an electron, and therefore can be said to have a small positive charge. When you put the golf ball into the hole, now it has a slight negative charge because it's temporarily holding the electron, which then you take it out and make room for the next person. So what we're going to see is that electrons move from hole to hole to hole temporarily, and it's this movement of electrons jumping in and out of holes, which is ultimately the current flow. Okay. A conduction band is a high energy level that the electrons temporarily enter when supplied with an external source of energy, a battery, voltage source. Since electrons cannot remain in the conduction band very long, they have a short lifetime, they will soon fall back down to a lower energy level, back into that outer valence band that we looked at a few minutes ago. When an electron is kicked or lifted into the conduction band temporarily, it leaves a hole, and many of them, with many electrons moving, and then it falls back down, it occupies a hole. Okay, so here we have the what would you use? It's called, right? This is the valence band. So this is the outer shell band orbit of the copper atom. This is a hole. These are the electrons, right? So by adding an external voltage source, this the electron in the outer shell goes up into this higher energy band, okay, right? And then it'll fall back down into a neighboring hole. So the amount of time it takes this process is known as the lifetime. And what happens is, with an infinite number of electrons moving from the valence band into the conduction band and falling back down, the holes appear to be shifting this way, while the electrons appear to be shifting that way. Okay? This process, recombination, is when the electron leaves the valence band, temporarily enters the conduction band at a higher energy level. So this is going to be and it's all energy levels, high energy level, and then it'll fall back down into the valence band. That is known as, it's recombining with a hole, so that's the recombination, is what it's technically called. Doping, we're adding impurities to increase the number of holes and electrons. We're going to add, and there's many others, different impurities we can add. There's two types of doped semiconductor. We have an N-type, and an N-type we use impurities with pentavalent atoms, which means there's five electrons. A silicon atom cannot contain at any one time more than 8 electrons in its valence shell. So that means then if we add in more electrons, those electrons can then be shared between two different silicon atoms. And that's what causes the current flow. Okay. In an N-type semiconductor, okay, the holes are called majority current carriers, okay, because there's only a few number of them, and the current carrier dominant majority is the electron. Okay, so N-type dopants, and there's others, but those are some of the all nasty stuff. Don't let anybody tell you semiconductors are green. I used to work in a semiconductor fab lab. All the nastiest acids and carcinogenic chemicals you can imagine. They're not green at all. It's all a lie. P-type semiconductors are created because they're doped to have additional holes. The impurities are trivalent, means it has 3 valence electrons, and they provide additional holes for the extra electrons to fall into. Okay. And in the P-type semiconductor, the holes are the majority carriers, and examples are aluminum, boron, and gallium. Don't add them to your dinner plate, please. Diode symbol. And there's many different types of diodes. So this is just a standard diode, and each one has its own symbol, of course. The arrow side is called the anode. The line side there is called the cathode. When a diode is forward biased, the voltage on the anode is positive with respect to the cathode, and a forward biased diode acts like a closed switch. This is not true, but it's approximately true. And I have that covered in detail in another video. And then reverse bias, it looks like an open switch where the anode is negative with regards to the cathode. Okay, so yeah, it's a very old drawing. So we have a DC source, a battery, we have a diode, anode to cathode, we have a little indicator lamp, and this is a current meter. And this is going to measure the current through the diode. So using conventional flow, the current goes this way. In reality, of course, electron flow, the current really goes this way. Doesn't matter which way you think of it. Nope. Okay, but a forward bias diode conducts current. That's the main thing to know. Reverse biased, change the orientation of the diode. The current here is approximately 0. There is a little bit of leakage current. That's covered in another video, but it's ideally 0. Okay. Forward biasing, okay. We have here, we have our DC supply, positive and negative. Okay, so this would be cathode. Okay, the my little plus signs here are used to indicate holes, and the little dashes are used to indicate electrons. This depletion region is the barrier between them, and for a normal silicon diode, when it's forward biased, we have a nominal 0.7 volts across the depletion region, which means this is ideally 0.7. Okay. More details in another video. Okay. Summary of operations. Electrons travel from the negative terminal to the N side. So the electrons in the N region are being repelled by the strong negative electrons charge on the negative plate on the source, and sort of kicking those electrons, kicking the electrons. So this negative charge here is kicking these electrons across the depletion region, and some of the electrons will fall into holes and recombine to form the current. That's kind of all that's saying. Okay. If you reverse bias it, that means the anode is negative relative to the cathode, or the cathode is positive relative to the anode, depending on which way you want to look through the window. Okay. Diffusion. So this is really at the manufacturing level, is at the initial time when they dope the semiconductor. These are metallized ends which the leads are going to be bonded onto. We have holes on one side, electrons on the other. Okay, and then the instant after they're formed, the electrons and holes kind of migrate away from each other, and that forms this depletion region between them. Okay. All right, so in that depletion region, that's separating the P and N side, or the anode and cathode side, if you prefer. The free electrons on the N side repel, and some will enter the P region. When this happens, a positive ion is created on the N side, absence of an electron. Shortly after the electron enters the P side, it will fall into a hole. Okay. This process will continue until the junction region, which is the interface between the N and P sections, becomes depleted, not 100%, but virtually depleted of electrons and holes. kind of like a no man's land, if you will, okay, where there's really only a few holes and a few electrons. To get the electrons from one side to the other, we need an external energy source. Once the depletion layer becomes thick enough, it's impossible for an electron to move through on its own. Some will go due to it's called electron drift, just due to ambient temperature, but it's insignificant. For silicon diode, that barrier potential is approximately 0.7. For germanium, it's approximately 0.3. Germanium is not used anymore, but I gather it's starting to make a comeback. Its main problem is it suffers from a much higher reverse leakage current than silicon. But it does have its applications. Okay, simple calculation. Okay, so this is a forward biased circuit. The resistor is being used to limit the current. So we have a battery of 10 volts. We have a forward biased diode with a nominal voltage drop of 0.7. Will it be 0.7? Probably not. That's a nominal value. There's a lot of variances, but 0.7 is the standard rule of thumb to use. So that's the anode to cathode. So if we have 0.7 volts across the diode, we have a 10 volt source. That leaves 9.3 volts across the resistor. It's just simply a series circuit. So the 9.3 and the 0.7 add up to the 10. Take the 9.3 volts divided by the resistor here, and something. This has been a very long time since I looked at this, so this should be divided by R, and something funky happened here. Divided by 100 equals 93 milliamps. Diode characteristic curve. So this is the forward region, positive voltage, reverse region, negative voltage, positive current, negative current. So you increase the anode to cathode voltage, and then at 0.7 volts, here at this knee, the diode starts to turn on. Diodes start to turn on. A standard diode starts to turn on somewhere 0.58, 0.6 volts. 0.7 volts is assumed to be turned on 100%. And then the current then increases linearly here, limited by the resistor. So over here then, maybe green wasn't the best choice to use. And the polarity is positive. Relatively speaking, positive to negative. I mean, let me go a different color. Okay, reverse region down here. Okay, so this is going to be then okay, that current then is ideally 0. So you see that little bit up here, that's the increasing leakage current, right? This breakdown voltage, that's the maximum reverse bias voltage. It's a datasheet value that the diode is rated at. You don't want to go beyond that. And so really the operating reverse bias range for a diode is in that region there. Now, diodes such as, see my other videos, the Zener diode, it's designed to be intentionally used in this reverse breakdown region. But a standard diode, it'll live there once and then that's it. Let's put it that way. Diode testing. Okay, you can use your diode check on your multimeter. When I first made this presentation 25 years ago, the testers weren't commonly available, but you can buy component testers. Amazon has them. $50. It'll measure everything. It's really quite amazing. But use the diode, check on your multimeter. It'll be 0.7 volts turn on voltage. It might be less, okay, but ideally it's 0.7. Okay, it starts to turn on earlier, maybe as low as 0.45, but basically, if you put the positive lead on the meter onto the anode side, and the negative lead on the cathode, if you get something, and this is like very, 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 very rough, to something like, then you know it's forward bias, it's working. That's what you expect. If you reverse bias it, that means then the lead placement is like this. OL means out of range. It does not mean overload. It's a personal pet peeve. Okay, that just means it's ideally infinite resistance, or the resistance between the anode to cathode is infinitely high. So you try, basically, what's the resistance across that? It's infinite. Okay. Packaging styles, again, they come in all different types, but this will be solid color. Again, this is a standard diode. If it's a small signal diode, they're normally pink in color with like a black stripe. Power diode, white stripe, black body. Zener diode, white, black, or black stripe. Body is gray, blue, bluish gray, something like pinky, something like that. Okay, the stripe end means the cathode. Okay, so that's the orientation that we're looking at. Okay. All right, surface mount goes on the top side of a circuit board, and there's several variations on this. And then power diodes. This is a big one. It's mounted on an aluminum heatsink for cooling. But anyway, there's different. They all work the same way. It just depends on the application. Anyway, thanks for sticking around, and we'll catch you next time. All right, cheers. God bless. Bye.